Well, hello everyone. This is our first video on Chapter 6, Applications of Integration, and we're going to look at areas between or more than two among curves. In Chapter 5, we looked at area under a graph. So if this was the graph between A and B, we determine the area, and this is f of x. We determine the area, if you remember, as the integral from a to b from f of x dx, and we use the fundamental theorem of calculus to identify and determine the definite integral, which was the uppercase letter representing the antiderivative of f of x evaluated from a to b, which really translates into f of b minus f of a. However, we didn't start like this. We started with a limit of the Riemann sum before we got to the definite integral. So basically what we see here is determined, first approximated for the limit of the Riemann sum before we look at the limit, with rectangles, depending on whether we're using the midpoint or the right point, leftmost point, rightmost point, it doesn't matter. So the height of any rectangle will be f of xi of that particular position, and this is the xi. And xi, of course, goes from a to b. So we determine the limit of the Riemann sum as being the area of the limit as the number of rectangles goes to infinity from the sum of all these areas of rectangles, base times height. Well, the base is always the same, delta x, and the height differs for the point depending on which xi we are at. So if we're at this xi, will be this f of xi. If we are here, it will be this f of xi. So f of xi. And of course, I goes from a to b, right? From the first rectangle till the last rectangle, n, and n goes to infinity. This was exactly the same thing with the integral from a to b from f of x dx. Same thing. This takes the place of the limit of the summation. Delta x is dx, and f of xi is f of x. Okay, so the same idea. Now, in this situation, we basically said, where do I find the area? Well, I find the area between f of x, upper function, and lower function, which is y equals 0. So we really didn't mention this. In section 6.1, we are going to do exactly, we're going to apply exact the same procedures. Let's say this is f of x. Let's say this is g of x, and we want to determine this area. How do I determine this area? Is the integral from, of course, the points of intersection from a to b, from upper minus lower dx. What is upper? F of x. What is lower? G of x dx. Now, of course, what happens if we have a situation in which we will not be able to, or we find that it's an easier way of integrating with respect to y? So let's say here's an example. And this is not a function. So this is x equals something in y. I'm just going to, so it's a function of y, because we're going to have examples in a moment. And here's another curve, which this one is a function. And let's say x equals g of y. How do I determine this area? Exactly the same. I have to determine the points of intersection. So between A and B, from lower to higher, from above minus below, or if you want, from above minus below. Same idea with the positive side. So then the area, this area now is the integral from A to B, from above, which is f of y, minus below, which is g of y, or if you want right minus left, same thing. Right minus left, but of course dy. So we're going to apply these principles and these ideas in a couple of examples to illustrate how to determine the areas between or more than 2 among curves. Okay, so let's take a look at, I'd like to start with 35 on page 443. We always have to graph, always graph. Always, find points of intersection. Okay, so in 35 on page 443, we are given y equals 1 over x. We are given y equals x. We are given y equals 1/4 x. And we are also told that we are only talking about the positive side of the x-axis. So first we have to graph, then we have to find points of intersection, and only then we integrate. Okay. So 1 over x is a famous function. We talked about it in Calc 1 over and over and over and over. Here it is. Getting closer and closer to the x-axis, of course. Doesn't seem like it's doing here. Okay, so this is y equals 1 over x, first function. This is super famous also. Let's graph y over x, y equals x. At this point, I'd like to find this point of intersection, setting them equal to each other. Y equals x and y equals 1 over x means x equals 1 over x. Cross multiply, x squared equals 1. And we have, when we take the square root or use the Pauli feature, whatever you want, x equals plus or minus 1. However, I have to make sure that all solutions are considered positive. So, or we're looking only for the positive solution. So then, obviously, this is 1. The y coordinate will also be 1. So that's one point of intersection. So this is done and over with. Now we have to graph the last one, which is y equals 1/4 x. Same thing, it passes through a 0, 0, but it will have a much slower increase, right? It's a slower slope. It's a smaller slope. It's 0.25. So I'm just going to graph it and then determine points of intersection. So this is y equals 1/4 x. We already know that y equals x and y equals 1/4 x, they absolutely meet at 0, 0. The other point of intersection that needs to be determined is between 1 over x and y equals 1/4 x. So I'm going to set these two equal to each other. Again, I cross multiply and I get x squared equals 4. In the same way, I get plus or minus 2, either taking square roots or factoring or the Pauli feature. Well, I have the same problem. I have to choose only x equals 2 because of the given condition in the problem. So then we already know that this is 2. What is the area in question? Right here. However, you notice that between 0 and 1, the area is found between green and purple, or brown, whatever this is. And the second half, so to speak, between 1 and 2, is between the red and the purple. So in order to determine this area among these three graphs, I have to determine or calculate two definite integrals. So the area, I'm just going to shade it in right now. Here it is. That's the area. Is composed of two definite integrals between 0 and 1, above minus below, of course, dx, and second piece between 1 and 2, from above minus below. At this point, all I have to do is just find the antiderivatives, and the rest, if it's just arithmetic, then we can use the graphing calculator. If not, then at least maybe one or the other can be determined quickly with a graphing calculator. So the antiderivative, x squared divided by 2 minus 1/4. Better even just write 3/4. I should have written 3/4 already, because x minus 1/4 x is 3/4 x. Same thing. However, between 0 and 1, and then plus, this is natural log of the absolute value of x minus 1/4 x squared divided by 2 between 1 and 2. Luckily, I can only plug in 1 here, because when I plug in 0, it's a polynomial. Everything will be 0. So then I have 1/2 minus 1/8. And then I plug in 2, natural log 2 minus 4/4, so this is minus 1/2. When I plug in 1, be very careful. When I plug in 1, I get 0, but I have to subtract. So it's 0 minus 1/8. So let's see what we get. So the 1/2 with negative 1/2, the negative 1/8 with positive 1/8, so final answer, natural log 2. And that is the area in units squared, whatever the units are, between, or I should say among, the three given curves. Between 0 and 1, a different integral, because the above function is green, the below function is purple, and between 1 and 2, the above function is red, and below function is purple. So there are two different situations here. Okay, so let's look at another example. And I was looking at 17 on page 443, in which we are given x equals 1 minus y squared, and we're given x equals y squared minus 1. Right away, we identify the fact that these are not functions. Good. So let's start by just to quickly go back over the steps. We graphed. We found the points of intersection, mandatory, and then we integrated. So the same thing here. Maybe we want to start with the points of intersection first. It doesn't matter. The order of these two is not important. Sometimes I prefer graphing first and then finding points of intersection. In this case, it doesn't really matter. So let's x and x. So then 1 minus y squared equals y squared minus 1. And then I subtract y squared. So negative 2y squared, I subtract 1, negative 2. So then y squared equals 1, which means y equals plus or minus 1. Good. So these are the points of intersection, right, for the y coordinate. So when I plug in 1, so x is 0. So the 2 points of intersection will be 0, 1 and 0, negative 1 for these two given curves, not functions. Okay, so what happens now when y is 0? So when y is 0, x is 1. When y is 0, x is negative 1. So for the first curve, when y is 0, we have x equals 1, so 1, 0. And for the second curve, when y is 0, x is negative 1, so negative 1, 0. We know that these are parabolas, but conic sections, either opening to the right or opening to the left, and depending on the leading coefficient, of course. Okay, so let's finally graph these. So we know that the points of intersection are 0 for x, 1 for y, 0 for x, -1 for y. Both curves have to pass through these 2 points. The first one, and also we know that the vertex will be on the y equals 0 line, which is the axis of symmetry of both. Okay, so the first one has the vertex at 1, 0, and it goes this way. Solved for x, x equals 1 minus y squared. The other one has the vertex at -1, 0, and it has to pass through the same coordinates. I will always present the axis of symmetry no matter what type of parabola or conic section it is, in other words, but there is no need here because the axis of symmetry is the x-axis. So this solved for y is x equals y squared minus 1. Obviously, the area in question is the shaded area. And let's see how we get this. So the area, of course, goes from, because we are going to integrate with respect to y, goes from the low value, which is y equals -1, to the high value, which is y equals 1, from right minus left, or if you want, above minus below. So the above or the right is x, so it's 1 minus y squared, minus below, which is, careful, y squared minus 1, of course, dy. So at this point, I have the integral from -1 to 1 minus 1 minus y squared plus 1 dy. I hope you remember from Calculus 1, every time I see a symmetric interval, I always check odd or even. The area cannot be 0, obviously, so it cannot be odd. So the integral from -1 to 1, from 2 minus 2y squared dy. I factor out the 2, and this is -1 to 1, 1 minus y squared dy. And I know that this is an even function. So twice times 2, the integral from 0 to 1, from 1 minus y squared dy. Do I have to do this? No, but it's a very important concept to review. Okay, so I have 4. I have y minus y cubed over 3 from 0 to 1. I plug in 1 because when I plug in 0, I get 0. So I have 4, 1 minus 1/3. So this is 4 times 2/3, or 8 divided by 3. And this is final. I hope these problems help you with all the work in this section.